Alrighty, so we are now looking at the properties of a confidence interval. So we've talked about what it is, what is a confidence level, and then we've actually constructed our own one sample z interval for a population proportion. But now we're going to look at what happens when you change certain factors. So we have this example here, and it says, how well are U.S. colleges run? This describes a survey of 1,031 adult Americans, and the survey was carried out by the National Center for Public Policy. And the sample was selected in a way that makes it reasonable to regard the sample as representative of all adult Americans, so we can probably assume it's a random sample. And of those surveyed, 567 indicated that they believe a college education is essential for success. So we're going to assume the conditions are met, and we could easily verify those large counts, 10% and random or representative. And we'll see that all of those conditions are met. So in class, I'm going to show you how to do this in the calculator. If you're watching this from home, you'll just use the Statsmatic applet, or you can calculate them by hand if you'd like to, but I'm just going to give you the answers here. So if I use a 95% confidence interval, I would find the following estimate. Now, using 95% confidence gives me 1.96. And the width of this interval is about 0.0607. Well, now if I go and use a 99% confidence interval, I get this new interval, and it's slightly wider. And I can wonder what happened here, but I see that since I increased my confidence level, the critical value also increased, and the width of the interval got larger. So if I compare my interval from problem 1 to problem 2, I could argue that as the confidence level increases, the width of the confidence interval also tends to increase. And we'll get into a little bit more as to the why shortly. But greater confidence means you have a better estimate. Now, you also have to ask yourself, though, well, isn't it wider? Isn't there more margin for error? And you might be onto something. So let's look here at the fourth case. Well, let's suppose we're going to use a different sample size of 2,000. And so now we're going to use a success count of 1099. And when I calculate the 95% interval with a sample size of 2,000 and a success count of 1099, I now get the following interval, and the width of this interval is about 0.04. Well, now let's look from problem 4 to problem 1, what happened? So here in problem 4, I increased the sample size, but I kept the proportion the same. And here in problem 1, I used a sample size of 1031. So it looks as though as I increase my sample size, it looks like the width of my interval is going to decrease. And well, let's think about back to sampling distributions. The more we sample and the larger the sample size, the lower variability we're going to see in the standard, in the sampling distribution of the statistic. Okay. Next up, let's do a new one here, going back to the original constructs. Let's construct a 95% interval with p hat equal to 0.91. So here my successes are 941 out of 1013. And I do so, and it looks like here's my new interval. And I'm going to have a width of 0.0317. Okay, now let's look here from the original problem to this new problem. So my width, as I increase to 0.91, got significantly smaller compared to the original interval. So what do you think happens the further we get from 0.5, right? Because remember, 0.5 is going to be a reasonable estimate, either does or does not happen. We're 50% confident what's going to happen there. So if we go ahead and increase the proportion, it looks like our interval gets smaller. So here are the key points for today. The properties of the interval. The higher the confidence interval, the wider the interval. The larger the sample size, the narrower the interval. And the further our estimate is from 0.5, also the narrower the interval is going to be. Now, 1 and 2 are going to be more commonly assessed on the AP exam. The third one shows up, but it is not as common. But nonetheless, you have to be prepared to use all 3. Now, why could this be? And let's think back to our form of a confidence interval. We have our point estimate plus or minus critical value times the margin of error. Well, the margin of error is the z-score times the standard error. And I know this is a standard error because it has p-hats. It's based on the sample. So if z is increasing, that's going to be directly proportional. The width should also increase. Now, if we can see here, the denominator is the n, and more specifically the square root of n. So the larger n gets, this will be an inversely proportional relationship, that the larger n gets, the lower this value will become, and then if I multiply z by a lower value, I'll have a narrower interval. Well, let's look at the opposite case. The further p hat is from 0.5, so like 0.91 times 0.09 is going to be lesser than 0.5 times 0.5. 0.6 times 0.4 is also going to be lesser than 0.5 times 0.5. So you can see here all the different mathematical relationships within this margin of error. Now, remember, the margin of error generally gives me this rough estimate of how wide the interval could be. So let us take a look at some examples here. So in your notes, go ahead and pause the video now. There's a few examples for you to look at. Go ahead and pause the video and figure out here which of these conditions will make the interval more narrow, and in the second one, which of these conditions would make it wider. So go ahead, pause the video, and try out here, and then we'll discuss shortly. Now, go ahead and review your answers. If I want a narrower interval, I'm going to want a larger sample size. I'm going to want a proportion closer to 0.5 and a lower confidence level. And I think I accidentally made a mistake right here, because if I want to be closer to 0.5, well, 0.3 is 0.2 away from 0.5, whereas 0.9 is 0.4 away from 0.5 here. So it looks actually as though I should 0.3 here. My bad. I didn't even randomize the answer choices. Whoops. Okay, now let's look here. If I want now a wider interval, I'm going to want a smaller sample size, and I'm going to want a proportion closer to 0.5, because that'll give me a wider value here. And it looks as though 0.45 is closer. Why does something feel wrong? And then a higher confidence level. So let's see, if I want a narrower interval, I said the further, the narrower. Oh, that's why something feels wrong. Okay, I was doing wider in my head. My bad. All right, there we go. So that was right originally. It's not a good teacher moment. My bad, y'all. And then a wider one means closer will give us wider. Okay, see? You see how I'm using my notes here in context clues? We're going to get through this together, I promise. But this will probably show up most likely in the multiple choice section. So you just have to be prepared to bounce between sample size, sample proportion, or confidence level. All right, now what actually is a margin of error? And here we know that the margin of error is a critical value times the standard deviation of the statistic or the standard error of the statistic. So if it's p and 1 minus p, that assumes I know the parameter. That would be the standard deviation of the statistic. But if it's p hat times 1 minus p hat, that's a standard error because it's based on the sample. So that hat tells us a little bit more information. And this margin of error tells us how far away the estimate of p hat can be from the actual p. So remember, I'm estimating the true parameter. I don't know the value of p. I'm just trying to guesstimate what it is based on some sample statistics that I've got. Now, remember, we need random 10% and large counts because if I look at this and I don't use a random sample, notice that the p or p hat is going to affect the margin of error. So if I use something like non-response bias, which changes my proportion, or response bias, or undercoverage, convenient sampling, if I use a bad sampling technique or introduce bias, the confidence interval can't tell the difference. It's just going to do what it knows how to do based on the information we provided. So that's why we want to make sure we have a randomized sample so that we can reduce the bias in our sample, as well as ensure that we can generalize to our population of interest. Because if I only convenience or voluntary response sample, it's going to limit my scope of inference. So just take that into account. Now, here's our margin of error. And if we are asked to find the sample size given a confidence level and a claim, we can probably do so. So I'm going to show you how to derive this formula. You will have to not memorize it. You have to be prepared to derive it if needed. But this is going to be the shorthand formula that you'll need. So the margin of error equals critical value times the standard error. I divide both sides by z. I get rid of the square root by squaring both sides. Then I want to solve for the sample size. So I'm going to flip here. I would cross multiply and then divide, which brings me to this step here. And then since I'm dividing by a fraction, I can multiply by the reciprocal. And I get that the sample size equals the critical value divided by the margin of error squared times the sample proportion times the complement of the sample proportion. And when we do this, we're going to round up just because we don't want to underestimate. It's actually a little bit better to overestimate here. And that'll just ensure that we've got, because I mean, realistically, you can't have like 53.64 things, but you can have 54 things or 53 things. And if we want a margin of error of no more than a certain value, remember this inverse relationship here. The larger the sample size, the smaller the margin of error, or thus the narrower the interval. Now, it's fine and dandy if we assume we know the parameter or a claim, but sometimes we're not going to know. And again, when we're guesstimating, we're just going to use a reasonable estimate of 0.5. Again, 50-50. So if I wanted like a majority of people, I would just say like more than 50%, etc., things like that. But 50-50 will be our conservative error or conservative value that we'll use. Now, here's an example for you, is that let P represent the proportion of students at Purdue University who purchase textbooks over the internet. How many students would have to purchase textbooks over the internet if we wish to be within 5% of the correct estimate with 95% confidence? So again, it was asking me what is the sample size needed, so I'm going to need N. It gave me my confidence level, so Z of 0.95 is 1.96. We want a margin of error of 5%, which is 0.05, and it didn't give me a claim about the proportion, so I'm just going to believe it's 50%. And I'm just going to use my formula here to get the following computation and then round up. If I use 385 students, then theoretically I should be within 5% of my true value or my estimate. So that's the idea there. You're just going to figure out your knowns and sub them into the formula. Now this has shown up on the FRQs, but most times it will also show up on the multiple choice. So I'm going to allow you now to go ahead and practice. So pause the video now, take a look at the practice problems, and then we'll go over them shortly. All right, so hopefully you got the following answer correct. And if you didn't, all good. We're going to do some practice with this in class. But that is the properties of a confidence interval. So we have to take into account the sample size, the confidence level, and the proportion that we're using to construct our interval, because this will ultimately impact the margin of error, and that'll tell us how much our sample can vary from the parameter. So a wider interval could be good, but it could also be a bad thing if we want to be more precise with our estimates. But nonetheless, we want to make sure that we are meeting our random 10% large counts conditions and that we are taking into account how we can modify our intervals here. All right, so that's going to wrap up our study of one sample Z intervals. And now we're actually going to start looking for significant evidence using what's called a one sample Z test for a population proportion. So stay tuned to learn how to conduct a significance test.